All right, so here we go. We've got L17b. I forgot the L up there. Anyway, this is lesson 17b. Energy equation examples. Let's go ahead and put an L in there. That never hurt anybody. All right, and so we're going to apply the energy equation in combo with continuity, momentum, hydrostatics, etc. So in other words, we have our usual tools. Okay. Here again is the energy equation. I have it just kind of like set out up there so that we can kind of make use of it and move it around and do whatever it is we want to do with it. Obviously, those ones are ins and those twos are outs. So here's what we've got. This is the last problem for the day. We've got a horizontal bend with an expansion joint. Okay, so the water's coming in somewhere, down here. Okay, and it's turning, and as it turns, it leaves over here. Notice this horizontal is a very key word because that means that this is not going up or down. Okay, this is a plan view, meaning we're looking down on it. Okay, so the z direction or gravity is going into the page. So that means that, which is kind of nice when the problem gives you that. That is a gift because it means you don't have to worry about weight. It means you don't have to worry about z, right? The z terms here are going to go away. So here's a z and here's a z. Those are going to go away. Okay, almost any point I choose, those are going to go away. Okay, the flow rate is giving as 5 cms. Okay, I made a point to call this CMS instead of meters cubed per second. So CMS is cubic meters per second. So that is the same as 5 meters cubed per second because I've given CMS on tests and that has confused my students. So I just want to make sure that you understand what that is. Pressure 1 is 650 kPa. Well, that's not really very useful unless they tell us what 1 is. And in this case, this is going to be 1 right here. Okay, which means probably I'm going to choose to make this 2. Okay, that makes sense. In fact, that's all kind of given in this problem. And it tells you that there's 10 meters of head loss through this bend, which seems like an awful lot of energy to lose through one bend. They don't exactly tell us how long anything is, so maybe it's not really that long. Anyway, so we're going to need, let's see, and what they want us to do is they find the horizontal force to hold the bend in place. So if I look at my tools over here, here are my tools. Let's see, we want the horizontal force to hold the bend in place. So that tells me that horizontal force to hold the bend in place, that tells me that my master is going to be the momentum right here. That's going to be the master. That's what we're looking for. Okay? So horizontal in this case, that is neither x nor y, but it is both x and y because we're looking at it from above. So that means we're going to end up with needing to do a free body diagram. Okay, and we're going to need to solve for the x force and the y force. And so our free body diagram is, in this case, of the pipe with the water. Okay, I guess we'd call it the bend and the water. Okay, bend and the water. Now in this case, it doesn't really matter because there's no gravity, so the bend doesn't really have a whole lot to say. But we're gonna, oh man, of course my hand slips as I'm drawing. It happens. So we're gonna go like this, and really bad drawing because this side is much wider, right? So we'll go like this, okay? And so this is 60 degrees, and here's my control volume. Okay, so now with my control volume, I want to draw the forces on it. And in this case, so this is the anchoring force. This is the force of whatever's holding the bend in place. This force is actually on the bend itself. And so this I want to call force of anchoring. So this is like somebody holding that bend. So I'll call that force anchoring in the x. So we'll call that fax. And we'll call this one force anchoring in the y, so phi. Okay, so those are the two anchoring forces. These are the things that we're solving for. In the meantime, what other forces do we have? Okay, as far as body forces, there's just a weight, but the weight is it's downwards. Okay, there is no downwards in this problem because we're only working horizontally, so we're not even going to worry about that. We're not even going to draw it. But we must note that these two locations here, right here, it is interior to a pipe, that is interior to a pipe. So they have pressures, and we cannot ignore those pressures. So we're going to go back over here, And let's draw those pressures. Now, pressures always push. So it's going to be like this. Pressures always push. Okay, and this is going to be P1A1. And this one's going to be P2A2. Okay, this is going to be P2A2. And I should go ahead and put the dimensions on here just so I don't have to refer back to the other drawing. So this is 0.5 meters. And this is 0.8 meters. Okay, so those are diameters. And what else do we need? Okay, the last thing that we need is we need to remember these momentum fluxes. So I typically draw them as lines that cross the control surface. So this will be V1, and this right here will be V2. Okay, so that's kind of a lot of stuff. Okay, so in order to solve the momentum equation in either direction, so I'm just going to kind of draw it in the general form, so it can tell me what all I need to look for. So I need the sum of the forces. Okay, so it's general in that I'm just going to give it arrows. Plus, okay, now we've got the sum of the ends, and of course there's only one end in this case, and that's at 1. Okay, the sum of the ends of rho v q equals the sum of the outs, rho v q. Okay, so what I'm going to do is I'm going to talk about kind of what we know and what we don't know. Okay, so the forces means I need pressures and areas. Okay, and let's go see what pressures and areas we know. Oh, okay, so let's see. We'll go back over here. Pressure 1, note, is given. Okay, so pressure 1 is given. Pressure 2 is unknown. Okay, the areas are easy enough to get at. Okay, so if we go back over here, we need pressure 2. Okay, A2 is basically given because we know the area. Okay, what else do we know here? Okay, these forces are things we're looking for. Okay, so we can go ahead and circle those. But we know how to find them because they're in this equation right here. They're in this term. And so those are the 4 forces. And then we know the rho because this is water. Do we know V1 and V2? Well, we know Q, so we can get at V1 and V2 using continuity. And we know Q. So basically, I need to get V's from continuity. So if we look over here, okay, from continuity, I can get the V's. So let's go ahead and do some asides over here. Asides. Okay, so let's start here. I need V1 and I need V2. Okay, and then I need P2. So those are the 3 things that I need to solve this. Everything else in this diagram I know. Right? Well, I mean, I don't know FAY and FAX, but those are going to come out of these 2 equations. You know, where, you know, that's 2 equations, right? Because it's going to be, that's really it in the X and in the Y. Oh, I should note, I forgot to put my little arrows in here, which are important. Okay, so anyway, what do we want to go for first? Well, let's go for the easy things. Let's go for V1 and V2. Those are a little bit easier. Those are going to use our continuity equation because we know Q. And we know that it equals V1A1. Okay, or V1A1, and that's an average velocity. So I can go ahead and solve this relatively quickly. I have already done this for you. So we can do this twice. And I'm just going to pause it and have it pop up for you because I think y'all have seen this enough now. Okay, so that should be fairly helpful for you right there. So obviously we need those 2 things. Okay, so we are good on that front. Okay, so now we know our V1 and our V2. We can even make those the average if we want by putting a little bar on top of them. And so that's good. There's no manometer, so we're not going to need a manometer on this particular equation. The geometry, well, we've already used that for continuity, but there's no Z's to concern ourselves with. So we're not really going to need that. But we do need to get at this pressure right here. And the only way that I can see to get at that is from the energy equation. And so that is a little bit annoying, okay? So let's go back. You know, we're still kind of in the sides. And let's go back over here, and let's use the energy equation, okay? So I'm going to go ahead and grab it, and I'm going to move it down here. And we're going to go ahead and solve it, okay? Or at least we're going to solve it for P2, okay? So nice thing is we've already solved for V1 and V2, so that kind of, you know, moves the buck forward there. And we know some things. So we know P1 is 650 kPa, so we want to be careful there. So we're going to have 650,000 newtons per meter squared. And that's going to go over the gamma of water, which is 9810 newtons per meter cubed. Okay, so notice we've got the units are going to work out, so this is all going to come out to meters. Z1 is going to go away, Z2 is going to go away. Why? Because it's horizontal. Okay, there's no pump between 1 and 2. There's no turbine between 1 and 2, so we don't need to worry about that. Okay, plus, we've got some alphas to deal with here. And I'm going to go ahead and put in a 1 for this right now, and we're going to double check to make sure that it's 1. But, I think it's going to be pretty safe to say here that this is going to be turbulent. We've got really high velocities. And so, let's see here. V1 was 25.46. Okay, meters per second squared over 2. G in this system is 9.81 meters per second squared. Okay, equals P2, which is what we're solving for, over gamma, 9810 newtons per meter cubed. Okay, plus, again, I'm going to assume that it's turbulent. Really, I'm just going to test this particular case at location 2 because this is going a little bit slower. I'm not really sure. We'll have to think about whether or not that's the better one to check. Okay, 9.81 meters per second squared for our G. And our head loss, we said there's 10 meters of head loss. So ultimately, that's kind of a lot of stuff going on here, okay? So if we solve this all the way, we'll get P2 equals 826.7 kPa, okay? So if it was asking for that, we would say that P2 equals, you could say 0.83 MPa, or really I think we'd probably say 827 kPa would probably be the preferred way to report that if we were reporting that, but this is the one we're going to use. Okay, so now we got P2. So now I'm going to go over here to my main equation, which of course, like a jerk, I kind of left where it would be in the way, so I'm going to move it below my asides. Actually, I guess I should go ahead and check those alphas. Let's check those alphas before we accept this answer. So let's go over here and let's check the alphas. Okay, so what we're going to do is we're going to check to see if the Reynolds numbers are greater than 4,000. And you know what? I'll go ahead and do it in both at location 1 and location 2. Okay. Again, I'm going to go ahead and just, I'm going to just pause it and have it just kind of pop up for you. And actually, I'll just stop right here, noticing we've got the velocity, the diameter, and we've got the viscosity, the kinematic viscosity at, I think this is at 20 degrees C, but basically, somewhere around there. And what I'm going to do here is I'm not going to bother plugging this into a calculator because what we're trying to do is we're answering the question is this greater than about 4,000? Okay, and hopefully you can see that 25 times a half is about 12, or let's say 13. 13 divided by 10 to the negative 6, that's going to be about 10 to the 7th. Okay, so that is much, much larger than 4,000. For this one over here, we can say the Reynolds number equals, well, 10 times 0.8 is about 8. 8 divided by 10 to the negative 6, well, that's going to be about, well, that's going to be about 10 to the 6th, okay, which is much, much greater than about 4,000. Okay, so both of these check that box, so it's turbulent and turbulent, okay? Now, you can plug that into your calculator if you like, but basically these numbers are way more than turbulent, okay? So that means our alphas are okay, which means we can accept this answer right here. Okay, so let's come down here and let's solve this using those numbers. Hopefully I can kind of keep them on the screen as we solve this. You know what, we'll just kind of scroll in and out to get it. So basically I'm going to do the x version of this equation. What we'll do, I guess, is I'm just going to put a little x right here. I'm going to put a little x right here. I'm going to put a little x right here. And I'm going to come in here with my eraser. And I'm going to erase these lines. Okay, because now we're just doing the x version of this equation. The other thing I'm going to do, because, well, let's ungroup. Let's duplicate. Nope. Let's undo that. try this again. Duplicate. Okay, so now I got another version of this. Is going to go right over here. That'll be my Y version. Obviously, we're going to have to we'll have to put some thought into that. But okay, I mean, we'll have to put some Y's over there. So I guess we can do that right now. And you know, there's a little Y right here. There's a little Y right here, and there's a little Y right here. Okay, so let's go ahead and let's start solving this sucker. Okay, what forces do we have in the X? We've got P2A2. We've got FAX. And we've got P1A1. And those are, except that has an angle on it. So that's going to be P1A1 times the cosine of 60 degrees. Okay, and then what else? Nothing. And then what about in the X direction? Well, in the X direction, we've got rho V1 cosine 60. Okay, that's V in the X direction times Q, which is going to be 5 cubic meters per second, equals, now what do we have out in the X direction? Well, in the X direction, we've got rho V2 times Q. Okay, so that should pretty much be everything there. So I'm gonna kind of just pause it and we'll plug and chug and have this all come out. Well, let's just, yeah. And that way you don't have to watch me zoom back and forth looking for numbers. Okay. Okay, it ended up taking a little bit more space than I had anticipated. But let's go ahead and zoom in and let's check everything. I warn you, there is a mistake here, so let's just look and see if we can find it. Okay, so here's P2. Okay, I put it in pascals, so that's newtons per meter squared. It's being multiplied by meters squared. So what happens there is they cancel and I end up with newtons. Okay, so that should be a force, which is good. Okay, FAX is FAX. Okay, P1 was given as 650 kPa, so that looks good. The area is in meters squared. Oh, it looks like I forgot a cosine 60, which was another error that I didn't anticipate. So right in here, I'm going to put a cosine of 60 degrees. Okay, and we note that that comes from the fact that the pressure is not pushing on this thing in, straight in the X direction. Okay, so then we go over here. Rho is 1,000. Okay, V1. Here's V1 right here. Okay, we note that that is kind of at an angle. So V1 is 25.46. It is at an angle. And Q is 5 centimeters per second. So if we check our units here, let's see here. We've got kilograms. Let's see here. This meters cubed is going to cancel with that cubic meters. And I got kilograms times meters and seconds squared on the bottom. So that's a newton, so we're good there. We're going to go over here, and we got V2. And V2 is right here. Okay, and we solved it as being 9.947, and we've got, and it doesn't have an angle, and we've got the rho is 1,000, the V2 is 9.947, and there you go. So the error, if you missed it, is right here. There should be a negative sign right here, because note that this V is a V in the X direction, so negative means negative. Just like this one over here, okay, it got a direction on it. This one also got a direction. This direction was a negative sign. This direction was a cosine. Okay, really, this direction is a cosine of 180, which is a -1, if you want to think of it that way. Okay, so if you do all of that, you end up with an answer here. A solution, if you solve for FBX, or excuse me, FAX, so FAX ends up being negative 592.7 newtons, or really FAX is negative 593 newtons, okay? Does that make sense to you? Okay, like if you're holding this pipe, does it make sense to you that you're gonna have to push to the left? So FAX equals 593 newtons that way. Okay, does that make sense? Well, let's think about it. Okay, the water's coming in, and it's got momentum to the right, and then it's turning back to the left. Now, what could cause that? The only thing that could cause that, basically, is a push in this direction. Okay, so the bend is going to have to push on it in that direction, which means the water's going to push on it to the right. The bend is going to push on the water to the left. You're going to have to push on the bend to the left to keep it from flying to the right. Okay, so that's why it kind of looks like that. Okay, so that makes sense. What about in the y direction? What's our expectation there? Well, let's see. The water's coming in. It's got some y momentum, right? It's kind of going in the positive y direction, and it's going to lose that y momentum because by the time it leaves, it has no more y momentum. So we'd be very surprised if we don't have a negative answer here. Okay, but let's go ahead and check that. Okay, so let's bring this down here, and let's solve it. And I'm going to do the same thing. I'm going to kind of pause it and plug the numbers in because I don't think that, well, let's set the equation up first. Okay, what are the forces in the y direction? Okay, well, we've got Fay, Fay. Okay, do we have any of those pressures? Well, P1A1, some of it is in the x direction, so sine of that's 60. Okay, what else is in the y direction? This pressure is in the x direction. So it looks to me like that's all we really have on this one, which is nice. Okay, what about in the y direction? Well, we've got rho of the water times V1. Now this one's got a sine of 60 on it. Okay, and then we got Q. Okay, that's good. Now what about leaving? Okay, do we have anything in the y direction that is leaving? And no, this velocity right here is not leaving. At least it doesn't have y momentum. So that's what we mean. This y momentum basically disappears. Okay, it just gets swallowed up. Why is it getting swallowed up? Well, because these forces are preventing it from doing that. This force is pushing it along in the y direction, so this one's going to have to push back. Okay, so it's going to have to basically eliminate that by being stronger than. It's going to have to neutralize this, and then it's going to have enough left over to cause that to basically go away. Okay, so let's plug in some numbers and let's see what we end up with. Okay, so yeah, it looks like it's going to be negative because all of these numbers are positive. We know they're positive because the velocity here is in the positive direction. The V1 is going in the positive y direction. And this pressure is pushing in the positive y direction as well. Note that that's the sort of thing that you play with as a professor to try to make the problems more interesting and make sure that your students kind of understand what's going on here. And this ends up being negative 154.6 newtons, or Fay equals, let's say, 155 newtons. Okay, so, or what, depends on how you like to write it, equals 155 newtons downwards. Okay, now the last bit of this, I'm not going to subject you to my work here, but we really want to know F anchor, okay? And so what we'll do is we'll do that standard thing where that standard thing, okay, where you find the magnitude and the direction. And so then you can say that Fa equals 613 newtons at, and this looks like this is going to be kind of in this direction, like that, 14.6 degrees. Okay, so there you go. Okay, 14.6 south of west. Okay, so that's it. That's how you do the energy equation. And this is an energy equation with a momentum equation on the tapped on the end. Okay, so these are wonderful problems because they make you use almost everything. There was not a pump or a turbine in there, but there could be in the future, and there wasn't a manometer, but other than that, it had everything. Okay, so that's this one. Again, take care of yourselves, and I'll see you next time. All right, hope all is well. Okay.